Yeah. Yeah, and I mean, if you want to run old games, the best thing is an old OS that never gets patched.
It runs on 10.
Yeah, well, they do, but they're probably better to run on Windows XP or 2000 or something. Well, virtual machines are usually too slow for gamers, and the graphics aren't good enough. So anyway, we've got Zoom good, and people are coming in. I'm supposed to hit mute all. So I thought I'd mention a few news articles while we are waiting for the official time, which would be about 5 minutes. And let me rearrange my windows so I can see what I'm doing a little better. All right. So there's been lots of stuff in the news. In my other classes, I've talked about this. There was Bloomberg published a report about a week ago now claiming that the Chinese have hacked their supply chain, or they're putting special chips on motherboards and taking over American companies' computers with it. And everybody in the know seems to universally agree that this is all garbage, and that they just got some sources that are lying to them because they're trying to sell them junk. But Bloomberg will not shut up about it. They continue to press this as if it's true, so it goes on. This is very interesting, and I'm only got a few minutes. That might be the one worth talking about. This is the National Cybersecurity Center, part of GCHQ, the British spy agency, and they have published an official report of what hacking tools are being used by government agencies to hack each other, the advanced persistent threat people, and it is very interesting. These tools, like here it is. It's not very long, 20 pages, and the hacking tools are not too surprising. This one I don't know about, J-Bifrost, a remote access Trojan. I got to check that out. And China Chopper, but Mimikatz, we know we're using it in this class. I've heard a lot about PowerShell Empire. And so these two I know about. This one's already in the class. I've got to look at these and see if they've been writing projects about them. Certainly, lateral movement frameworks are very good going through PowerShell, but of course, just Windows systems. But that's usually what you want to move through anyway. And here's an obfuscation tool. So I got to check these out and see what I can do about adding projects about them. Whenever I see reports like this, I try to make sure I'm hitting all these things, and we're not yet. Like, I never heard of this. And so you're checking out and seeing what they are. All right. Anyway, let's see what else might be fun. I was surprised that Washington State has declared the death penalty unlawful on their state constitution, and apparently this has survived court challenges. And if that's true, we could start having individual bans on the death penalty the way we have individual bans on abortion state by state. And that would really change America a lot, because a lot of people, like Amnesty International, almost every other civilized nation, says that America is wrong with the death penalty. And we might see some progress in getting rid of it if the individual states knock it off. And I think it's always been state by state anyway. And this guy got 6 months in prison for helping the Russians interfere with the election, but he didn't hack anybody. They paid him to make bank accounts in his name and then give them the credentials so they could use them. So he was basically like a money mule. This is a common thing they do. They have Americans make accounts to move money in and out. And so now it's essentially money laundering. And he was convicted by Mueller and sentenced for, I don't know exactly what crime it is. Maybe it's espionage or something. Maybe it's money muling, something of that order. Not a very huge punishment. And kind of fun, but not too important. It's all right. Yeah. Oh, yeah. Well, here's something that's probably pretty useful to understand AI and the limitations of AI. Amazon made a recruiting tool to pick the best candidates from people applying for jobs, and then they trained it on all their historical jobs, like who they hired, and of course, it's now reproducing their previous bigotries and who they got hired, right? Because without them telling it to pick on women, it said, well, the ones that women don't get hired, so get rid of them. And of course, that is the thing. Your AI will just learn to do whatever you show it. So it will reproduce whatever your training material did. This happened to Microsoft. Microsoft put an AI on a chat room, and everybody, as a joke, started talking with swear words to it, and it rapidly learned to swear horribly, and they had to take it down. I mean, your AIs are just like babies. You train them and they learn an environment and then they do whatever they've been taught to do. So, oh yeah, yeah, that's the thing. So I mean, that's the thing with AIs. They learn whatever you train them to do. And so I think this is why a lot of people pick on Hollywood, because all Hollywood casting is always stereotypes, because they just try to reproduce what the average person expects to see. And, you know, it's a problem. If you're trying to alter society, that's the opposite of what they're doing. They're trying to reproduce it the way it is.
Well, that's the thing. Some of those stereotypes are so ingrained, you don't know they're ingrained.
That's right.
So but the minute somebody tries to like buff the stereotype or add more representation, they say, "Oh no, you're being politically correct." So well, you're trying to program us. I'm like, no, you're already programmed.
Yep.
You know, that's the thing.
And this is I heard an interview with the woman that made Crazy Rich Asians. And she said, "This is a great movie." And they went to the studios and they said, "No, I don't want this movie. There's no Americans in it." She said, "They're all Americans. They're just not what you think Americans should look like." And he's like, "We know what I mean. They're not real Americans. They're not getting anywhere." Yeah. Yeah.
As an American movie.
Yeah.
And it's like, oh, they're all Italian.
Yeah. Yeah.
Yeah.
Yep. Anyway. Yeah. So anyway, so let's pick up with programming. Now, of course, you're not going to learn to do any real programming in this class. We're not covering that stuff. And there's a whole department over there where you can learn C and Java and JavaScript and all that jazz, and that's fine. And by the way, you should learn at least one programming language if you're going to be any kind of technological professional, including a security professional. If you don't know any languages, most hackers prefer Python. It is the easiest one to learn and quite powerful. But anyway, even if you don't write the programs, our role is to find the security problems in the programs, because for some bizarre reason, the current state of affairs is people get degrees in training and programming, and they learn to write dangerous, vulnerable code. And they typically have no clue about security, and they are never taught or expected to know anything about security. And they hire a second team of people, of us, to patch the holes they create. That is the current arrangement. It is very strange, but that's the way it is. Yeah.
So the textbooks are really outdated.
Well, that's a very interesting statement you make. It's not fair to say the textbooks are outdated. They have the latest features, but they typically have no security. The authors and the programmers and the teachers and the students have no interest in security, and I understand why. I've talked to them about this. If you go to, I've gone to teachers, the most innovative teachers I could find in the CS department. I talk to them, and they say, "I can't add security to my class. Security is a huge topic with a bunch of books. I don't even know it myself. I've got enough work to just teach them how to program." And asking them to learn security at the same time is crazy. That's another whole field. So that maybe it's even true. And Dan Kaminsky, who is, you know, one of the leaders of this field, thought leader by far, he said, "I don't expect programmers to learn security. What you should do is build a programming environment that automatically puts in the security, so they don't have to think about it, because they got other fish to fry." And that's the thing. They have to make it fast. They have to make it small. They have to make it have all the features and keep all their version control going and everything. You know, they have a whole universe of stuff just to make it work at all. And expecting them to also do security is probably not reasonable when security is so big and complicated. Yeah.
Are compilers going to have security?
Well, that's a very good question. Are compilers going to do it? And the answer is, that is one way to go, is to put more security features in your compiler. That is what Microsoft did. And Microsoft was the king of all this. Microsoft completely ignored security as an official policy until 2002. Then they had the Trustworthy Computing Memo, and they started paying attention. And what they decided to do was they did train their staff in security flaws, but then what they mostly did was modify their C compiler and their C libraries to make it less dangerous. And that has worked. They also have a large security team, and they try hard to fix things, but I don't think they expect their primary programmers to be terribly aware of security, although I'm not entirely sure what happens inside Microsoft. But I think this is currently the issue. It's one thing about security is it's always full of a lot of people yelling that everyone else needs to do their job differently. And I think the security community is beginning to wake up to the fact that this is not helpful. This does not work. To call people idiots and say other people are all just wrong to do what they're doing. The fact is there are reasons why other people are doing things, and trying to secure it, trying to make it safer, you don't get there by blaming it on somebody else. It's not very effective. Anyway, So we'll make some simple programs here and see some simple flaws. So the point of programming is you have these things called all-purpose digital computers, which are relatively new. And very strange thing, computing used to be a human profession, and people would sit with paper and add and multiply and take logarithm tables, and it was just a job. They would do like accounting on paper. And then we had the automatic digital computers started for the military, and then we had the general purpose computers that we have now, where it's so cheap and so powerful you can write a program in a relatively easy language to do something, and now you can do anything you want as long as you can specify the exact flow of steps. Do this, then do that, then do that. And that's where we are. The problem is, turns out to be very easy to make mistakes in giving those instructions. And so the mathematicians have been through the philosophical, conceptual mathematics of this, and they have figured out what programs can do and what they cannot do. And there's a group of problems called NP-complete, which can be solved by a current computer, which means it is possible to have a recipe, a series of steps, do this, then do this, then do this, and you'll get the answer. That's a current, I think it's the NP-complete language is one that can do that. And any language with these three features can do any program a computer can do. Although it might take longer on one piece of hardware or software than another, they all have the same space of problems they can solve. They have to have branching, looping, and testing. Now, the original programs just had that in a very simple way, things I used to write like old Fortran and stuff. Then it turns out that you couldn't maintain code that was written that way. It was spaghetti code. You'd have thousands of lines and then go to and jump and jump. And then when you try to modify it later to add new features, you have to like put stuff in the middle and patch it in from the sides, and pretty soon you've lost control and it's all full of bugs and everybody hates you. What turned out to be useful, I have structured programming where you write a little function that does one thing and there's a self-contained unit. And you'd solve little problems, and then your main program would call one function and call another function. Now, if you need something new, you just write another function or modify an existing function, and you have a controllable small set of changes, and you can test one module without testing the whole thing and get the bugs out of it place by place. So, all right, branching is when you go from one part of the program and you decide to run some other part for a while and then come back. Don't necessarily come back, but in practice, usually you come back. Looping is doing something over and over until some condition is true. And testing is some kind of if, where you can decide whether to do something based on a condition that can change. Those are the three things you need. So here's the simplest C program. The general structure of C programs, you have to have a main. Main tells it where it starts. It has to know where it starts. It does not necessarily start right at the top. So main indicates the place where it's going to start. Then everything in C uses these curly braces to indicate a module of code. So you have an opening curly brace here, and everything until the closing curly brace is main. That's how it works. And white space means nothing. You can run it all on one line. You can put in tabs, carriage returns, spaces, anywhere you want, which I was totally used to doing. And when I moved to Python, I was very annoyed because you can't just do that in Python. And at first, I didn't know that. So I tried to write it like C, and I kept on fouling up on me. And I saw indentation error. I said, what do you mean indentation error? Indentation don't mean anything, but it does in Python. And you typically have to include libraries. That's what that include does. You include code somebody else wrote. This is what makes it easy to write C, as easy as it is, although C is relatively difficult to use. This is what makes it really easy to program in Python, because there are libraries that do everything you could possibly want. So all you have to do is include the library and then do a couple commands to call a library function, and you can do any simple task with just a few lines of code. So this will just print hello world. And you can put comments in with the /*. You can put extra code. This is very important and required by professional programmers, because hackers and people that are hobbyist programmers write one program and there's only one person working on it, and then they don't really need comments. But if you're working at a company, you have many people writing code, and you have people who are hired to take code that was written by someone before them and understand it and maintain it. And then you really need clear comments, so you understand the purpose of this code, where it fits in the system, who I should go to ask if I have questions, and all that. So branching and testing is here, and this is the essence of what we're exploiting in the 127 class. So here I have a main routine. The main routine prints a message asking you for your age, and then it does the scan routine to read in an age from the keyboard, and then it has an if statement. So I'm in main, then it has that printf statement. So it has to stop executing code in main and transfer code down to printf, execute a printf, and then return. Then it has to go to scanf to read input from the keyboard, execute that, and then return. So this process denoted by these arrows, where you leave the main routine and you go into a function, and then you leave the function and come back. That process is the branching, where you move from one part of the code to another, and that turns out to be very vulnerable in C. This is mainly how you take over the machine right here when you return from a subroutine. It turns out that while you're executing this code, you can overwrite the return pointer, which tells it how to get back and cause it not to go back, but to go somewhere else, like to run code you injected. And that's how you take over the machine with buffer overflow and with other ones, memory corruption vulnerabilities. So then there's looping. Looping in C is fantastically complicated to where an enormous number of people get it wrong. And it's true of all modern languages. I don't know why. In the 70s, there was a language called BASIC that had a very simple way to make loops, that it was very easy to use, and it went extinct, and they replaced it with the current method, which nobody can understand. So this starts at 0, continues as long as I is less than 11, and then increments I every time. So how many times is that going to print that statement? Any votes? 12? 11?
Less than 11.
Less than 11. Well, how many?
So because it's less than 11, it's not 12.
So how many times is it going to print? 11. 11. I think 11 is the right answer. Let's see if we got any coming in. But it's hard to tell. And people do get it wrong a lot. Let's say I had a chat coming in. 10. Good. There's someone. So let me just put that in. I might as well do it. So let's see if I do. Let's put in loop.c. I'm running this in Kali Linux. Same thing here. Those easy. So include. Whoa. Got to spell it a little better.
I mean, the comment says
All right, main int I 4. Okay, 4. Let's see. I guess I'm I equals 0. I less than 11. I plus plus. Print F. I'm going to say print number %d I. There. That'd be more easy to count. And now we're done. So that's my program. Except I intended to have a number there instead of a 3. Not that it matters that much, but there, that might be a little more clear. Okay, so let's see. I say Y, enter, then GCC loop, and put the output in loop. Okay, it complains that I didn't specify what this should return when it was done, which I didn't, but it's only a warning, so I can ignore that. Okay, 0 to 10, so that's 11. So it is 11, and the point is, this is one of the many common errors in C. Very often people get it wrong, and there is an off by 1 error, where it does something an extra time or 1 time too few, and that can lead to total system compromise. That could be the routine that removes dangerous characters from input. And it forgets to remove dangerous characters from the last line of input because of this, and so you can sneak them in, that sort of thing. Yeah. Yes, this is what all modern languages naturally like to start from 0, and that is weird. And anyway, you could start from 1, but by tradition, everyone's expected to start from 0, and they're off by 1 frequently. So this is true of quizzes that teachers write, and English syntax and everything else. There are certain words that are hard to spell, so people spell them wrong. There are certain questions phrased strangely, so people get them wrong. There are certain parts of the language that are hard to understand, so people make the mistakes there frequently. And this is one of them. So anyway, an algorithm is the general series of steps you go through to solve any task. Every program has an algorithm, which is the abstract logical flow of what it does. And bugs are errors in the program. You make mistakes, everybody makes mistakes, and they cause the program to do something unexpected. You can start writing your algorithm in pseudocode. Yeah.
There's a difference between bugs and errors, right?
Not really. No bugs or errors. There are many different kinds of bugs, though. I mean, some bugs are just typographical errors. Some are logical errors, where this is what happened to proof of work coin, which was Ponzi coin, which is going to be, it's a project coming up at the end of extra credit project. They made a routine that would have a investment scheme, right? And there was a method where you could transfer money from one account to another. And then if you transferred money into the fund itself, that was the same thing as your investment routine. And they transferred the function down to use the investment routine. But the investment routine assumed there was only one address involved. but the transfer could in principle have up to 3 addresses involved. So there were conditions under which the transfer routine would move down to the other routine and actually withdraw money from the wrong account because they didn't know how many accounts could have been in the original request. And that's the kind of bug that is hardest to catch. It's not a typographical error, it is a error in the assumptions you make. This module down here assumes the problem has 1 address. This module up here has 3 addresses, and when you move from here down to there, they weren't careful enough about exactly what gets passed down here. That happens all the time, and it happens, for most extreme example I know is SQL injection. SQL injection has been with us for 20 years. You write PHP code that takes data from the user, then it sends a request to a database to see like what their stored address is in the database, and the database gets a command, and it doesn't know what that command was supposed to be. So if you put in a funny address with punctuation marks, you can change your command, which should say, tell me what my address is, into say, delete all the records in the table. And the database server gets that command and executes it and doesn't know anything is wrong because it does not know that you don't have the right to do that. And the C code, the PHP code doesn't know. So this is where there's not exactly a bug. There's not one line of bad code. There's just a chain of command where one unit does their job and passes on the next unit that does their job, but misunderstands the commands. So now you've got a disaster, but no one part of it is broken. That's a very common problem, these logic flaws, or where you didn't think about certain problems that could happen. Another common one is the flow in shopping carts. You have stage 1 where they buy an item, stage 2 where they fill in their name and address, stage 3 where they fill in the credit card, stage 4 where they buy it. Well, they can jump from stage 2 to stage 4 and get the product without giving the credit card information because you didn't really force them to go through exactly those steps. This, again, it's not exactly one line that's wrong, but there's a flaw. This happens a lot.
So it's not as simple as I read this.
Yeah.
Yesterday.
Yeah.
But the program still runs. An error, the program.
No, though I think they're both essentially the same. I mean, a bug is just a bug's an error. As far as I know, they mean the same thing. But there are many different levels of them. Anyway, so here, yeah, go ahead.
I'm sorry.
Yeah.
In Kali, how do you make the window bug again?
Control plus, Shift Control plus. Yeah, very important on the Windows machines. Anyway, so pseudocode, if you want to shop stuff, you can write pseudocode. If you're more formal, you can write these things called flow charts with these triangles and stuff, but you can just do it with pseudocode as well. So you're gonna cook food, cook lunch. So you have a purchase ingredients function, which will then call get car, drive to store, purchase these items. And now I'm done purchasing ingredients. Then I can go on to prepare ingredients and cook and all that jazz. This is what you do. You take your job and break it up into little modules and then write little functions that do smaller jobs and piece them together to make the big job. And there has to be documentation if you want this stuff to be maintainable. The most irritating thing for programmers is to inherit code from somebody else and now you have to fix it. This is a big problem. Very, very often it is easier to just rewrite the whole thing yourself than to figure out what in the world they were thinking. I've even had it happen to me, which I think is a fairly common experience, that I write something, and then a few days later when I want to fix it, I have no idea how it works. It doesn't make any sense at all. I cannot remember what the point was and looks like an idiot wrote it. This happens a lot. Anyway, so bugs are errors in the code, and the industry standard is 2 to 3% bugs, which is hard to believe that anything could run that way. Windows 2000 was better than that, 60,000 bugs, 1 per 1,000 lines. Linux is even less. 6 times less on average for the versions that are out. Yeah. Well, no. That's a very good point. Patches, no, the bugs are caused by the original programmer because the way you really program is you have something you're trying to accomplish, you write some code, you compile it, the compiler gives you some errors, you run it through some tests, the tests find some errors, then you say I'm done, and it goes to production, but you really never found all the errors. You went it through some amount of testing, but it was never enough to get all the mistakes. And especially in Windows, which is the all-purpose operating system running on many different pieces of hardware with many different versions of other things installed. You see, lately, Microsoft had to pull their Windows 10 patch, and then they had to pull it again because they write it, they think it's okay, and when you actually deploy it to millions of people, it turns out for some of them, it's not okay. There are some conditions under which it does something horrible, and they were unable to find that in testing. And so the patches patch some bugs and bring in new bugs, of course, because there is no option to have perfect stuff. So anyway, so yeah.
Linux has less chances of errors because they're more focused.
I'm glad you bring this up. That has been the traditional statement, what you said, that the Linux programmers are more motivated and focused and they write better code. And everyone believed this, a lot of people believed this, until 2014, when we had it spectacularly proven false by Heartbleed. When the open source code had a disastrous error, and Heartbleed meant that all your data, all your supposedly secure servers were wide open to the world for 2 years if you used Linux, but if you paid for your software from Oracle or Microsoft or Apple, you were fine. So just like you would think, there's nothing so simple as Linux is better than Windows. What it is if you are careful at using Windows, it's very good. If you're careful at using Linux, it's very good. And if you're sloppy, they're both dangerous. There's no simple answer like use Linux and you'll be safe. No, you need to be good at using Linux or good at using Windows. You have to pay for quality. And then either one is fine. They're both all full of mistakes, all full of problems. You have to constantly patch them. You have to have enough sense to not use the dangerous things from experience. And you have to put other layers of defense in your network because you know that all your servers are going to have some malware sometimes and some other problems. So that's what you do. You can't trust anything. The zero trust model. You don't trust any of your stuff to be 100% perfect, which really shouldn't surprise anybody. You don't trust any of your employees to be 100% perfect, or any of your locks, or any of your suppliers to be 100% perfect. Everything is only good to a certain point, and you should trust but verify all the way through. Yeah.
That Heartbleed. What were they? So they got the source code and they just started going through it?
No. What happened with Heartbleed is the HTTPS protocol, which is responsible for all the secure servers in the world, the encryption library for it, someone decided to add it turns out some connections would time out and lose their connection. So they added an optional feature called a heartbeat to it that would automatically send a message back and forth every 30 seconds or so just to keep the connection alive. And when they added that feature, they made a mistake in the code. And the mistake was you would send a message to the server like a ping, which is the heartbeat, and it had a length field in that message. And the server would repeat the data back to you that it got from you, but it didn't check the length. So you could send it only 10 bytes of code, but you could put 64 kilobytes in the length field. And then it would take the 10 bytes you sent, followed by 64 kilobytes of other stuff, and send it back to you. So you could get random data from the server by lying to it, because the programmer didn't think that you might falsify the size field. And that meant you could get fragments of what the server was showing other people, fragments of their pages, fragments of their input, and under certain conditions, you could even get the primary secret on the server, which is the encryption key. So now you can break into everything. And that turned out, the problem with it was, not only was it, you didn't need any authentication, but there was no logging of this process anywhere. So when it happens, they said for 2 years, we've all been using this buggy module, and nobody can say how many people exploited it because there's no log to look at. So you have to go to your boss and say, we forgot to lock the door. We have no record of who came in for the last 2 years. We will never know whether all our stuff was stolen or not. And how about that raise? It's just not going to work very well. And people say, where did this code come from? They say, well, some random guy in Finland put this update around at Christmas when he was probably drunk, and nobody checked it for 2 years. And he said, why are we using this stuff? And everyone and the world asked, why are we using this stuff? Maybe Bill Gates was right all along that you ought to pay people money to write professional code instead of this open source model where some random guy writes it and you pretend that some other guy audited it when nobody actually paid them or made sure they audited it. So, it's...
I always believe that open source, that you leverage the power of the community, everybody.
Yes. Well, see, this is why it really gets down to the fundamental clue of how society works. In capitalism, you work for a boss, and the boss makes you work, or he fires you, and then you have these sort of nice brotherhood hippie model where everybody just contributes out of the goodness of their heart. But that's the open source model has always been the code is there, anybody could check it, so everything will be fine. But the fact is, why would anybody check it? That's a bunch of work. That's pretty boring. Nobody gets to make an exciting blog entry that said, "Hey, I checked the Linux module today, and it was just fine." You're not going to get a lot of hits from that. You're not going to get a promotion from that. You should. This is like in science. There's something that needs to be done is repeating other people's experiments just to show that they work. This is important, but you'll never get a promotion or a professorship or anything from it, so it doesn't happen much. It's, this is a fundamental issue in society. The innovators get the rewards, and the people that sort of clean things up and shore up what's already there don't get the rewards. And so that's why in the capitalist model, you have to pay them. And then they pay a bunch of people to do this boring work. Okay, test this on every system, test it with every graphics driver, go through every line of code, boring things.
Basically, everyone thought somebody uses it.
Yeah, that's it. Why would anybody do it? They put it up there, then they pretend it's great because anybody could audit it. But the fact is there's no process to make people audit it. There's no paycheck in it. It's and they claimed that system was working better. And sometimes it was spectacularly better. And of course, before 2002, Linux stuff was much better than Microsoft because Microsoft specifically said security is a waste of time and we're not wasting any of our money on that. So that's where it all started, of course. At that time, there was a very good reason why Linux would be more secure than Windows, but not really anymore. And in practice, it's not any more secure than Windows anymore. They both have about an equal amount of disasters and mistakes, and forward you go. And now, out of this, an independent group of people did make the job of auditing the cryptographic libraries. And now they audited OpenSSL and other things. There's a group of Linux people that formed a committee of volunteers to start auditing stuff, which is what needed to happen. This unglamorous work got more attention after a big disaster. So C is how it all started. Back when I got in this game long, long ago, mainframes had a brand. You would buy an IBM mainframe, and it would come with 8 telephone books full of IBM material, and you would learn how to program the IBM mainframe language, and that was it. And if you got a VAX mainframe, you had to learn a whole different language for it, and on it went. Each mainframe had its own proprietary language, and this was pretty stupid, so they decided to create Unix to be the unifying operating system so everybody would be the same. And therefore, in order to write Unix, they had to have a language to write it in, and they created C. C was the language to write Unix in. And now, if IBM or anybody else made a mainframe, all you had to do was write a C compiler in their language, and then you could compile Unix and run Unix, and now all the computers would be the same. And therefore, you could have the internet because they would be talking the same language and able to send signals to each other, and that was what everybody wanted. So the internet was a Unix production, and it worked quite well. And C was designed to be very fast and very close to the raw machine language, which is why it's so dangerous. C is not C is not like a car with an automatic transmission. It's like a car with a manual transmission. It's even more like a car that you build yourself from a kit. It assumes that you really understand computers. You really understand exactly what's happening, and you just want to make it a little easier to write the code. But it started with people that were very close to the hardware, and they didn't think about a generation of programmers that have moved into an abstract space and really don't understand the hardware very well at all. And so it's easy for modern programmers that have never built their own stuff to make huge mistakes in C. The assembly language is a lower level language. Assembly language is a language that lets you write specific instructions that compile directly one-to-one, are translated directly one-to-one into machine language instructions. So you'll have a command like push 70H. This will take 1 byte, 70 in hexadecimal, and put it on the stack. Then you can push this on the stack, then you can call this routine there, then you do XOR of EBX with EBX, which will put a 0 in the EBX register. Those are assembly language instructions. Each one of them just moves 1 byte around. And it takes thousands of them to do anything interesting, like open a window or take keyboard input or make a network connection. And so writing this is very, very burdensome. It will take many programmer hours to make anything big happen, but it is very close to the hardware. And what really happens in the hardware is it runs a machine language. And the machine language is just raw hex code, raw binary. This turns into binary, and that's what the machine sees. All the machine works is binary machine language. But assembly language is the attempt to make raw machine language readable by humans. So it turns it into this stuff like push and call and move. This is assembly, yeah. And the raw code is just a series of hex like this. These are addresses. The hex is not showing in this dump, but the raw code the machine uses is just a bunch of hexadecimal bytes. And so you need a compiler. If you write in a high-level language like C, so I had to write this thing, then I had to compile it with GCC because your processor cannot run C. It can only run machine language. So you have to take the high-level language of C and convert it into machine language, and that's what compilers do. All right, so you make this thing in a text processor like Nano or Notepad on Windows. Then you put in your comments if you like. You have the include statement at the top that brings in libraries. Standard I/O is what you need if you want to use print and scanf, and there's many other libraries for math and graphics and everything else. And then you can make functions with these curly braces. You have the name of a function like main, and then the curly braces show where it starts and stops. And you can call other functions. It's like printf and scanf. This will call printf, then scanf, then printf again. And functions can call other functions. You can go many, many layers deep. And that's what the stack does. And then you can declare variables. This is what makes it a structured programming language. There are other programming languages where you can just use variables without declaring what they are first, and the computer will guess, like Python. You can just say a equals 1, and then you can say a equals hello. It will say, oh, I guess you want it to be a string now. I'll turn it into a string. And then you can make a equals 1 plus 3. It'll turn it back into a number again. You'll figure that out. C will not do that. You have to tell it what it is. This is an integer. It can only hold the number. You can put numbers in there. If you try to put text in there, it will crash. So that's the, or at least you'll get some kind of error. So there's integer, there's floating point numbers for math with a decimal point, double precision. There's character values that hold 1 byte, which is intended to be a printable character. And there's strings that hold a whole bunch of bytes terminated with a null at the end. And there's many other types of variables. Yeah, double means double precision, just longer. The integers are longer, and if you use float, it's long for integers, and your double means more decimal places are kept. So it's just more precise and bigger. So I++ here increments I by 1, and integer plus plus just adds 1 to it. It's a shortcut for I equals I plus 1. And you've got plus is the unary operator that you can put plus or minus in front of a number to indicate if it's positive or negative. The plus, plus, and minus, minus, add and subtract 1 from it. And you've got multiplication and division and modulus and all the mathematical operations are, of course, available. And you got logical operations. You got I less than 11, which compares this to that, and the result is called Boolean. It's either true or false. You can have Boolean variables that are just true or false, 1 bit essentially. Although it takes a whole byte to store them in hardware, just for convenience, because addressing 1 bit is too difficult. But in fact, there's only 1 bit of information in there. It's just true or false. And you can compare things with equals equals or greater than or equal and so on. And all right, you can combine operations like here, if A is greater than 5 and B is greater than 5, then do something. You can have compound conditionals. All right, I got a few cahoots about that stuff. And that's as far as we're going to go in productive programming, but this is a breaker class instead of a builder class. So now we're going to start making bad code and messing with it. So I guess I can run it this way. That'll do. Oh, good. And the Kahoot is already, Zoom is already running. So the remote attendees should be able to see these. Yeah, you can even see the screen in here, which is pretty good. Okay. I'll start a document to record the winners in. All right. Trump's bad wig. Well, it's apparently not a wig. I've seen people explain how he has to get up in the morning and glue it on and stuff. Yeah. Is it a wig? Oh, is it too bad? Okay. I heard some people say it was just a massive promo. It was actually real hair. I don't know. It's, and then glues it on with hairspray or something, you know. You know, you could just be bald anyway.
I don't know. I've seen a Photoshop in bald.
Yeah, well, it makes a huge difference too. He might not be president if he didn't look good on TV. It's right. It's. He might. Apparently, he knows how to look the way he needs to look. I mean, Tammy Faye Baker. I thought she looked terrible. She was very, very, very famous. You know. these TV personalities get a look, and they work, and often it's not a look that you think is good, but it happens to work. His style is to offend people anyway. He's not really trying to, you don't admire him because he's beautiful. He's intended to be shocking and offensive. That's his thing, you know? So I guess his look is appropriate for what he's doing. Anyway, I guess we can go here. So which one of these do you not need in a programming language? Right. Inheritance is a property of modern object-oriented languages, but you don't really need that. It is just a convenience in the organization. The other three you need. If you don't have the other three, then what you have is not a programming language. Like HTML is a markup language. You can change how things look, but it doesn't have branching, looping, and testing, so you can't do math in HTML. It is not a programming language. All right. So what is 2% of your code? Bugs, okay. All right. Which language came from Bell Labs in the 70s? See? And it's all free because it was funded under a government grant as a research project, so it was all given to the world for free and started the whole free code thing with Unix and everything. All right. What language is in the microprocessor? Okay, it's machine language, not assembly. Assembly is there for humans to read to make it easier to understand machine language. Machine language is all the processor keys, just raw bits. And you can write directly in machine language, and I used to do it. Back in the ancient times in the 70s, I used to write in base 10 assembly with poke command in BASIC on the Commodore VIC-20. That's it, because that time it was 8-bit assembly. It was very simple. There were only 100 instructions. There were really only 6 you ever used. You could just memorize them and poke them in. Remember, 169 was load A9, load the accumulator. It was pretty simple, and you could learn the basics of assembler, and it really hasn't changed that much. All it did is the words got bigger, but there really are only 3 or 4 things you can do with a byte. You can put it in memory, put it in a register, increment, decrement, do an XOR, add and subtract. It's really not that many things to do, and nothing has really changed. Anyway, so how many times will this thing print A? Okay, that will be 9 because it starts at 1 and it counts as long as it's less than 10, so it goes from 1 to 9. All right. But you see how hard it is. All right. So I've got a few winners, and I guess we'll take a 10-minute break. It's just 10 minutes to 7. We'll pick up at 7 and then talk about code with bugs in it. And I'm going to record the winners. All right. And I'll stop the recording. I'll leave the share going, though, because we'll have a 10-minute pause. What's that? LibreOffice is, of course, different. The main thing people notice is it has many fewer features. It's like Office from 10 years ago. And as to whether it's safer or not, I've never seen a head-to-head comparison. I think nobody really knows. They all have bugs. But LibreOffice, the problem with LibreOffice is Oracle bought it a few years ago. And everyone is very unclear how much it's being developed or whether it's going to be abandoned and stuff. OpenOffice. LibreOffice is the open source alternative because they got so upset about Oracle buying it. So I'm not quite sure what its fate is. Anyway, so let's make a buffer overflow. I got one here. So if I do this, I got this thing called hello. So if I look what's in hello, it's this. This is the classic buffer overflow. So I set aside space for 10 characters, then I read the name and I don't tell it any length limit on the name. So if I run that, and my name is Sam, it's fine. but if my name is longer, then it crashes. Now, this is what you get for using an unsafe language like C. You can set aside room for 10 characters and then put in 20, and it will not complain. It will just do that stupid thing. The reason it does it is because it's trying to be fast. So up here, this statement reserved 10 bytes of data and gave a pointer called name that points to the first byte. And when it goes down here to put something in there, it has forgotten how big it was supposed to be, and it does not check. All this does is read data from the keyboard and start at the location called name and put in all the data until the end. And it doesn't know or care how long it is. That's your job. Its only job is to most efficiently take this one line and turn it into machine code, which it does. I can take all the data you give me and put it starting at name, that's it. And if it was longer than 10, that is not my department. So you're able to overrun 10, and then if there are more variables down here, you could leak from this variable into the next variable and change other values you weren't supposed to be changing. And if you go far enough, you hit the control variables that are used to return to the main system, and then you cause what's called a segmentation fault, where you have tried to use memory outside the allowable range. And typically what you've done is you've overwritten the return pointer, so it tried to resume code in the calling routine, and it was unable to return back to Linux properly because you destroyed the pointer that led back to resuming code in Unix. Yeah?
And so they just, anything right after Charlie just disregards, if you will, the very top.
No, not at all. No. What happens is all the code takes effect, and when you compile it, it's put there. But when you execute it, this code gives you only enough room for 10. See, when you enter a routine, it sets aside room on the stack for temporary variables. It figures out how much room you need, so it'll make 10 bytes per name, and then maybe another 16 or 20 bytes for overhead. And it sets aside that much room, and that's called your stack frame. And that's all the memory you have for your process. And if you put more than 10 or 20 bytes in there, you will overwrite control structure that is being used by other parts of the program. And in particular, you hit the return pointer, which is used to return from a module. And so the code will run, and notice something here. It took that name and it printed that name out. It was able to use it. It stored it and it could use it. What it did was it put 20 bytes and a null terminator here, and the next routine was able to take that pointer and send it to the printf routine and use it. It was able to store the data. So the fact that you overran it did not mean it crashed at this point. It can keep going. It's only going to crash when it tries to use the data stored after this. In fact, let's try something else that's even more fun. Let's make hello 2 here. So if we're on the track, let's copy hello. Hello 2.c and nano hello 2. Okay, let's do this. Let's have another one. There, name 2. And let's print this, name 2. Let's see how this works. There. So now I got to compile it. GCC hello 2 and put the output in hello 2. Okay, it gave me a warning, but no errors, so it will run. So I can run it too. Okay, and my name is Sam. Okay, and so I initialized. Now let's do that cat of this program. This shows you a few other interesting things. Okay, whoa, okay. Oh, actually, this is good. This is the binary. And the binary is unprintable garbage. If you look at the source code, that's what I wanted to show you. And now let me run it again. Let's talk about it. If I give it Sam, okay, what happened here is I defined 2 spaces to store data, 10 bytes here and 10 bytes here, but I only told it what to put in the first one. So here, it read in Sam and put it out. Here, it disclosed information I was not supposed to see. It printed whatever was in that location, which I did not initialize. This is what happened in Heartbleed. You were able to get it to send data that you did not specify first. So some other random data was sent to me, which I didn't put there. So that could be leftover data from before. So that's one thing. Now, the next thing is, if I put in a longer name, then I'll eventually be able to overwrite the second one, I assume, although they might be stored in the reverse order. Yep, I wasn't able to hit it. I'm able to cause a seg fault, but I think if I do the second one, let me just copy hello through, and then I'll go back to the plan stuff here, but this is worth doing a little bit, to hello 3.c. Okay, if I read into name 2 here, instead of name 1, and compile that one. hello 3, and there, that's what I got to do. There, that'll do it. Okay, now hello 3. I put in Sam, and now the name is down there, and this has some weird thing left over from before, this third stuff I didn't put there. And if I put in longer than that, then yeah, this is the whole name, and the last few characters went there. So I leaked from one variable into the other variable. So if I do this, maybe more obvious if I do this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. See, the B, C, D went in that variable, and it all went in this variable. So I leaked out of the reserve space for the first one into the next one, and it did not crash because I didn't hit anything really important like the return pointer. But if I put in a little more, it'll crash.
Are they always stored next to each other?
That's up to the compiler. That's a very good question. I stored next to each other. Notice they were in the order other than what I expected. The earliest compilers would just put them in the stack exactly in the order you declared them. Then Microsoft found out about this, so they started putting the arrays always at the end, so that they overrun, they won't hit other things. That was their smart compiler switch. And there are various theories. But no version of C that I know does anything like put a real mark at the end so it knows if you've overflowed, which would be nice. Things like Visual Basic do that. They do something so they know if you're overflowing. So if I put in more, now I get a whole variable here, the second part here, and now I get a segfault because some of this junk hit something important. So I broke it when it tried to finish and return. But I was able to keep running. And this is what bugs do. They don't cause a crash right where the bug is necessarily at all. They cause some damage and it crashes later. Anyway, that's good. That's the classic buffer overflow. And so here's how you exploit a buffer overflow. We're doing lots of this in the 127 class. So what you do is you have some vulnerable variable like name with some limited amount of space like 20, but I'm able to put in more. So you put in a lot, like 1,000 bytes, where it only expects 20, and you put in any kind of junk until you hit the extended instruction point. There you put in a special controlled number, then you put in more junk, and you put in some NOPs and an egg. The egg is your payload. That is the code you're trying to run, typically a shell that lets you execute commands on the server. And you can just generate those with attack tools like MSF Venom. So you have an egg you're trying to run, you put all this junk in as the name, you put in the NOP sled, and then you try to guess where this egg is. So you have to load a copy of it on your machine and practice and use the debugger and stuff to try to see what part of memory it's in. And if you can figure out where this is in memory, you know what address to put there. And then when it tries to return to the stored instruction pointer, instead of going back to resume the other routine, it'll jump into your code. And the reason you use the NOP sled is to make your exploit more reliable, because you don't really know where it's stored in memory on the server, typically. You try to build your own imitation, but it's not perfect. So if you put in an NOP sled, like 1,000 NOPs, then if you can even guess within 1,000 of the right address, NOPs do nothing. They're a perfectly valid command that does nothing, so it just does nothing, 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 egg. So if you can hit anywhere in the NOP sled, you win. And that's typically how buffer overflow works. You inject code, and it all relies on the computer not knowing what it's doing. I'm putting in stuff that was supposed to be a name. It was supposed to be readable text, but instead I put in bytes that can be interpreted as machine code and executed. And the computer, which doesn't know what it's doing, does not know that this should be text, not executable code. It can just interpret it either way. There was a funny demonstration I saw 10 years ago. I forget what it is. You could open Notepad and type like 10 characters, a simple command, just a few characters as like an insult about George Bush or something, and save it. And then when you ran that file, it would do something else, because the same bytes that were readable text could also be interpreted as commands. And that's what happens here. So in order to prevent these buffer overflows were the original main black hat trick that a guy named Alex Null wrote them in Frack magazine about 25 years ago, and a whole generation of hackers learned how to do this. And it was the #1 way to take over Windows machines for about 10 years, because all the code everywhere is full of this error. And Microsoft finally fixed it around the time of Vista. After the 2002 Trustworthy Computing memo, Microsoft really tried hard to fix all their security problems, and they put in these defenses to stop it. And so here's one of them, is address space layout randomization, which came out with Vista. In the old days, you would just load your machine, and it would just take the first block of available memory. So it would start at 0, you'd load Windows, then your antivirus would load, then your web server, then your SQL server. They'd just stack up in the most logical way. And that was fine, but what it meant was it was pretty easy for the attacker to build a similar server and tell where he was in memory to do the attack. So address space layout randomization just takes all those things and randomizes. Every time you restart, it puts this one down here, that one up there, that one over there, all random places, so you don't know where your code is. So now, even if you're able to inject code, you can't find it. This was actually extremely successful. It stopped a whole generation of white hat attackers, the ones we know about, for about 2 years. There's an influential conference called CanSec West, where they had the Pwn to Own contest, where they bring in the latest machines, they boot them up, and people try to take them over. Now, all they're going to do is go to a website. You have to take them over through the browser, and if you do, you win the machine, and you get prizes, and everybody, and they compete, spend all year developing them, and they were not able to get into Vista at all. They spent the whole first day, everybody tried their best attack against Vista, and they couldn't get in Vista. And the second day, they downgraded to XP, and they were able to get in there. Because this defense stalled the white hat researchers for at least a year. They couldn't figure out how to get past it. They eventually found ways to get past it, but their existing techniques were not good enough. And that meant that whole generation of malware before this point was all nullified. Yeah?
Is this pseudo-random?
Yes, it is pseudo-random, and so one possible attack would be to predict the random numbers. Now, that is not one that worked in practice, but yeah, that's a good thought. And in fact, there is a similar related way to do this. It turned out that the way Microsoft actually implemented, in many cases, there were only 10 or 12 bits of randomness, which is only something like 1,000 options. So all you had to do was run your attack 1,000 times and you'd get lucky, because it wasn't really random enough. So that was one weakness of the system. Anyway, so another defense is data execution prevention, which has been included in all motherboards for more than 10 years and was now included in the Windows operating system. And that means you could now, remember I said the fundamental problem is the computer doesn't understand what it's doing. It does not know that these bytes should be an image, these bytes should be text, and only these bytes over here should be code. And that's what this addresses. You can mark areas non-executable. It's a permission, which means this is not executable code. Even if it looks like executable code, do not run it. And that's what you should do for parts of memory that have things like text and images and stuff. And you can do it now. When you reserve a block of memory to be used by your code, you can say this is non-executable. And in fact, the security model of Windows is you should only be allowed to have write permission or execute permission, but never both on the same segment. So nothing that changes is executable. This will end self-modifying code, and it will end anything variable from being run. So any place where you take data from anywhere will not be executable. That's the idea. And that's the point. This whole area is marked non-executable. So now even if you make a mistake, you can overflow the buffer and you can inject all this stuff. You can go, it'll go to the end, it'll execute this, and use this address and go to here, and it will stop on a NOP. It will hit a NOP and then stop and say cannot execute a NOP. That is your sure clue that you got data execution prevention turned on, because there's no way it cannot do a NOP. There's no possible, the only reason you can't do a NOP is it's in non-executable memory. You can't execute any commands at all. And this is another very strong defense. All right, so then there's a canary value. We've been all modern, for 15 years, you've been all operating systems. So the way the stack frame is organized, when you enter a routine, you set aside some memory for local variables up there, like name and other variables, and then the registers. And then you have the stored instruction pointer down here at the end, and you put a canary value in there, a random value. And when you try to return, first you check the canary to make sure it has not changed. And you only return if it has not changed. If it has changed, you stop and say stack smashing detected, I quit. Somebody has been messing with data down here they were not supposed to be changing. And now this whole process of changing the EIP will not work anymore. It will catch you because of the canary value. And again, one of the many attacks against it is under some conditions you can predict the canary value and replace it with the right value, but when things work correctly, you can't, and this makes it impossible or extremely difficult to do a buffer overflow of the classical type. So those are the general defenses that, and there are specific attacks against each of those, but that's what always happens. All you have to do, the cops get bigger guns, so the crooks get bigger guns, so the cops get bigger guns. You know, no defense is ever perfect, but these greatly strengthened Windows and killed off a whole generation of attacks. And all the modern attacks have to use more complicated tricks to get through these defenses. Yeah. Yes, modern versions of Windows have all three of these things. And Linux too. Yeah. Anyway, and now even the Mac. The Mac is the slowest to adopt these because the Mac had a very small malware problem. So they did not bother to put in these defenses until long after Windows did. And people would complain. They say people think they're safer on the Mac. You actually have less defenses, but there's also less people shooting at you. So, you know, but the most sophisticated defenses are in Windows. It doesn't necessarily mean you're safest using Windows because the most sophisticated attacks are there too, but it certainly, they put far more money into defending Windows than any other operating system. Anyway, so then there's HTML. HTML is not a programming language. It just describes how things should look. So you make your page in Notepad or any text editor, and all it has is these formatting tags that start with less than and greater than signs. So you have header tags to make text big and break tags and bold and italic and such. And your source code all looks like that. But when you render it in a browser, it now makes some font big and some italic and bold and all that jazz. It's just a way to format things. Then there's Perl. Perl was written specifically to handle text processing. You're reading a bunch of text, and now you have to format it, break it up into fields and such. This has been around for a long time. I don't know if it's that common anymore. It used to be really common. Now it's considered, I think, kind of old-fashioned and not taught that much and used. It's still around, though. It has, yeah.
Why is there a book that's almost common?
That's a good question. In my opinion, they should probably cut out the Perl. I think I told them that. You'll see I got credit in this book as a technical editor, and they did not take all my suggestions. But one is you should really get rid of the Perl and put it in Python, but I think the author knows Perl. And there's a generation of people like Perl. There's people that tell me you need to learn Tickle too, which is the coding language used to program Cisco routers. And you know, both of these are pretty much niche languages and really old. And the red versus blue that I did at CactusCon, you had to write a script in Tickle. And it's done by some router administrators, but you know, there's some people who think it's important, but it's pretty old stuff. So I wouldn't push Perl too much. C, I think, is far more important. And PHP and Python. Those are hot. Yeah. And JavaScript. JavaScript's really hot. But Perl, I think, is on pretty tired and old. Anyway, so you can run Perl here. And but one thing about it is you got to get used to a lot of languages. Everybody always writes a new language for every stupid thing they're doing. So you can't have just one language. Once you know one, though, they're all pretty easy. They're minor variations. But every blockchain product has its own language. It's just ridiculous. There's R, there's Go. Everybody just has to write a new language for everything. The quantum computers have their own languages, like 3 of them. I don't know why. If they'd asked me, I would say, just write a Python module and make everything Python or something. But everybody writes their own language for every case. It drives me nuts. But anyway, that's where we're at. We're the slave of industry, not the master of it. So we have to adapt to what's really going on out there, even when it seems unnecessarily cruel. Yeah.
You said they're all alike with minor variations.
Yeah.
What are the categories, so maybe look this up some more, but what are the things that usually change when they make another language? What are the things that are most these minor variations?
What I've seen is they always mess around with what makes a variable. They sometimes put a special character like $$ in front of a variable, and sometimes they don't. They mess with exactly what the header of a routine is, and they like to mess with white space, which is very annoying. Yeah, but they make weird decisions, and then you have to learn their weird thinking. I don't know if I have a good answer. It's surprising though. Like if
you were learning from one language to another,
yeah,
and you knew that okay, you need to look for these 12 things that are going to change.
Yeah, I know that would be good. I'm not aware of that, but in a way, it is certainly true that after you do 3 or 4 of them, they all seem like pretty much the same thing.
Well, that's a good example of the dollar sign. What's the point of that?
The point of the $, which you see in ASP, is and in PHP, is that you know what's a variable and what's a keyword. See, that all started back in the days of MS-DOS. You had things like con is reserved for console commands. You can't name a file con. You can't name a file LPT1. Those are reserved words. You're supposed to know certain words are reserved. So now you have a sentence that has like Fred or not Bill. And you're supposed to know that or and not are commands and Fred and Bill are variables. And some people are very offended by that. They say that's confusing. The variables should all have $ in front of them so you can tell what's a variable and what's not a variable. And maybe that's right. In a way, that's kind of logical. But they make decisions like that. And like C, you put a semicolon at the end of every line because white space doesn't matter. So it doesn't matter how many carriage returns or tabs, it could all be on one line. Other people say, like Python, why do we have these stupid semicolons? just indent things correctly. You should indent them anyway so you can read them. So you have to indent them a certain way. It's, you know, some developer has an idea and they make it their way and everybody follows them. It just seems to me unnecessary. You know, like I said in the last class, people were commenting online about this. I said, you shouldn't make your own operating system. Whatever you're doing, just use Linux or Windows. You don't need to make your whole operating. I would tell my staff, if I had staff, you can't write your own language. I don't care how you think the one thing you're doing is unique in the world. Use a normal language. There's,
On the other hand, pretty much assures that you don't persist attack.
oh, no, I don't think it prevents you from attack. It might make it possible to copyright your stuff. That might be one argument, but I think it's really just ego. Somebody thinks my way of writing stuff is so much better than anything that's been done before, and I really don't think that's likely to be true. Most likely by now, one of the standard things is pretty good enough that whatever wrinkle you're putting on it is not worth what it's going to cost to make everybody learn a whole new language to do whatever we're doing here. But, you know, maybe I'm just one of those conservative people holding back progress by tying them to the past. That seems to be the way it is. Everybody seems to write a new language every month or two. That's the way it's going. And web developers have to know like 10 or 12 languages these days. That's the way it is. Yeah.
Speaking of the dollar sign,
Yeah.
is there a specific name for that?
As far as I know, just a dollar sign. Yeah, the other ones have weird things. Anyway, so you put sub in front of subroutines in Perl, and variables begin with dollars, and ampersands call subroutines instead of using call or something. So it looks like this. This is a subroutine, and this calls the subroutine speak. So this is what made sense to him. This is weird, you know, mighty weird. Dollars word is a variable, ampersand speak is a subroutine, and you just have to know that. Instead of, you know, this is the kind of cruelty they do to you.
Because it's C, like you just
Yeah,
put INT.
I know. And you put parentheses. And in Python, you just put parentheses, and then it's a subroutine. But here, you don't. It's like, this is what he thought made sense. And so you have, it's like learning a foreign language, like French or Japanese. You have to learn how they do it. And they do the same thing very differently, and it can be pretty frustrating because it's not terribly obvious why they have to do the same thing another way, but that's the way it is. Except this is all artificial. Somebody invented this just a couple decades ago, so they could have just been whacked on the head by their manager and said, knock it off, just use Fortran or C or something. Don't invent some weird crap. That's what I would have done. But anyway, that's what for loops look like, pretty much the same as C. And you have testing conditions in Perl. And, you know, anyway, so there's many other languages. Now, there are general categories. The original languages were not even structured. So you used goto all the time. And that was such a bad idea. That's pretty much over. Although I think there's a few constrained conditions in which you still write that way, like on microcontrollers and in BIOS code and stuff, where you really have old stuff. But anyway, that's pretty much over. Even assembly code has call now. But see, then the object-oriented is the next level of abstraction. This was really important. Now you can define an object like an employee, and the employee can have a name attribute and a pay attribute and a promote method and a demote method and put on vacation method. There's a data structure that has code and data in one object, and that's called an employee. And then you can make other objects based on the employee. Like you can make a location that has several employees and a door and all this. So you can define these abstract data structures. That's what these modern languages do, like C++ and C# and all that. You can make larger abstract quantities and manipulate them as larger abstract quantities. This turns out to be really useful to model real cases that you have to handle. So you have classes, so you have an employee, and then you have the get employee method of the employee that will take a parameter like the employee number, and this will now get that particular employee so then I can get their name and print it on a check or something. And so here's the class you might have. It'll have first name and last name, and then it will have methods. So the data structure has, it's called an object, and the object has attributes and methods, which is active code that does things and static data that just sits there. And that is all the object. And you can have objects made of other objects, and you can have whole groups of objects that are imported into a different program. And it's a way to make code portable and reusable. And this is very important. That's the way it's really done for almost everything now. Yes, absolutely. You connect to databases, very similar thinking. Yeah. Anyway, and so then there's Ruby. Ruby is what Metasploit was written in for a while. I think it's now written in Ruby. I'm not sure, but anyway, here's Ruby. Ruby was written, it was very, very hot for a while, and Ruby is just very logical and organized. And you see, it doesn't look that different than other languages, but it has a somewhat different structure, and it was really quite popular. And anyway, these have many languages, and generally the goal of a language is to try to make it easier to do one use case. There's some situation that's easier, but you can go the other way. You can make languages that are intended to make it difficult, just as a joke. So they wrote lol code. I don't know if you guys have seen the lolcats. The lolcats are these cartoons, these pictures of cats with jokes. So here's lol code. This is a real language. You can get a lol code compiler. You begin your program with hi, and you end it with k thanks bye. You make a loop. I has a loop. I has a variable. I'm in your loop. I'm out of your loop. Up variable. Bang. You have, this is the code. You can write whole programs in this, because remember, all you need is branching, looping, and testing. You can do it any way you want. So people make these joke languages where any kind of garbled language can be used. And then there is a whole category of esoteric programming languages. You can do lol code here. You can do it online. Yeah, yeah. And then there is brainfuck. Brainfuck is the king of the esoteric programming languages. Now, and to be, that's why I'm glad to teach adults, so we don't have to try to avoid the bad words, because hacking is full of bad words. And because it basically is closely connected to crime and the military, polite language is not a priority in the world of hacking. So anyway, brainfuck is the original Turing machine. The original Turing machine was never built. This is what defined the mathematics of computing. The Turing machine was a theoretical thing Turing invented to understand what computers can do. And you have a line of bits, and you have this thing sitting on a line of bits like a snail, and all it can do is change the bit underneath it or not change it, and then it can go left or right, and that's all it does. And it wanders around like a snail, click, 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 changing those bits, and that's all it does. And he did the mathematical analysis of what kind of problems that thing can solve, and that became the model of modern computing theory. And this codes that process. So there are only 8 possible structures, and they're all done with punctuation marks. So this increments, this moves to the right, that moves to the left, this increments and decrements the thing under the byte you're pointing to, this outputs it, and so on. So that is brainfuck. It has a total of 8 structures, and they're all punctuation marks, so that is hello world. Sit on the first byte, increment until it's an H, now move to the right, increment this one until it's an E, then put output somehow. You can write whole programs in this language, and it is designed to be very, very difficult to write and read them. And there's a whole series of these. There's another one called JSFuck, which I had to do in CCSF, and I made a project in one of my classes based on that. It took 64,000 bytes of code to print like a 10-character flag. It is very, very inefficient. But I don't even understand how it works, but you can write JavaScript that is nothing but punctuation marks, just parentheses and square brackets and braces, and somehow that can be interpreted as bits that are adding and subtracting like this, and thousands of nested punctuation marks turn into text in JavaScript. I know you can do it in Bash, and you can do it in C. You can write a line that has no variables, nothing but punctuation marks. It has that capacity. Just no one who is even remotely sane would ever use it that way. But it is technically possible to write code like that in a language. Yeah.
Was that just for a novelty, or it had a purpose?
That's a very interesting question. And the question is that a novelty, or does it have a purpose? And this is where you get into like mathematics. I mean, it's playing with it, but it means in a way it is a challenge to get you to understand it. You know, if you learn to read this, then you really understand computers at a deep level. So this is where, in the whole world of mathematics and philosophy, it is actually a very hard question. Are you really getting anything done, or are you just playing games? Well, in a way, playing games is how you get things done in mathematics. Like most mathematics is involving bizarre sets and stuff that have no practical application, and yet sooner or later, someone will come by 10 years later and use that, like Hilbert space is an infinite dimensional space, which is just madness, and it turned out to be super important for quantum mechanics much later. So you have these people just playing with the concepts, spinning up webs of madness, and then some of it turns out to be important. Yeah. Game theory is a similar activity. Game theory is the mathematics of figuring out how to win at games. And It is super important for military games and for economic models and everything else, but it started out again as just a thing. They were like the guy that in A Beautiful Mind, that guy who had some kind of mental disease was revolutionized game theory by finding ways to win by accepting a second order victory and choosing certain people will lose so other people can score more. He developed basically conspiring to defeat games, which is super important in politics and in a lot of places. So I mean, this is what happens. The philosophers are doing something and a bunch of practical people say, you're just wasting your time playing games. They say, I'm changing the world. And sometimes that's true. And often it's true that what they're doing is just wasting their time doing nonsense that will never have an application, but you don't know. So it's not simple. Anyway, these are mental exercises, and there's a bunch of them. Yeah.
Did you ever take something like this and actually make it run?
Yeah.
So it's almost kind of like encrypted.
Yes, it is. It's just technically called obfuscation. Encryption is where something is scrambled to where it is actually impossible to get in there without the code, whatever current level of impossible is. Obfuscation is where it is hard to read, but there is a way in.
So what if you obfuscate it and encrypt it? And so it's just extremely time consuming.
You can do that. But in general, what happens in the world of cryptography, most people say, oh, real cryptographers sneer at obfuscation. They say, don't even waste your time on that. That won't really stop anybody serious. You should use real encryption that will really stop them. But there is a huge argument. In fact, I'm going to be giving talk about this at the club later and down at the conference. This is a lot of people, in fact, just obfuscate stuff when they should be encrypted. One thing that happens a lot is a lot of amateurs will do stuff like this to code, and their boss will say, okay, it's encrypted, and they'll ship the product, but they didn't actually encrypt it. They just obfuscated it, and that turns out to be a disaster because people can get in. That's the problem. Most levels of management aren't smart enough to know the difference, and that's the big difference. This is like hiding a key under the mat. You know, that's what obfuscation does. There's a trick, and if you don't know the trick, you can't get in. But that's not the same thing as encryption, which means even if you know exactly what's going on, you still can't get in, which is much stronger. Except, of course, everything has mistakes and holes. Sometimes there's a hole in your encryption routine. But in general, the point of encryption is that even if you know everything, you still can't get in, unless you really have the key. Anyway, I got some cahoots about that stuff. And that's the world of programming as far as we're going to go into it. So that should be here. These are very good questions. You're asking just the right thing, you know, and we're all struggling with this. Well, how should we be writing code and how should we be securing it? Nobody really knows. If you saw Richard Boo's talk at the club, it was unbelievable. He had slides with like 100 brand names of security products that people are paying tons of money for all this stuff, and of course, none of it works. They're all getting hacked anyway. That's why they have to make so many of us. The reason there's a huge boom in our field is that we're all really terrible at what we do. You can hire all these security people and you still get hacked. I think when I saw this article last week, there's 8 billion records have been stolen this year alone. Like 2 records per human. It's ridiculous. And a lot of really smart people are working really hard to protect stuff, and it is totally not working. So in short run, it's jobs for all of us. I would assume in about 10 years, we're finally going to build some security device that actually works, and then they won't need so many of us, and there won't be such a ridiculous situation out there, but I don't know. We don't have it yet. Maybe it'll be AI firewalls. We're already getting those, but the bad guys are going to write AI attack tools. So we maybe just become bystanders as the robots duke it out. Oh, yeah. Maybe we'll have Terminators wandering around blasting each other in the streets while we hide in the basement. You know, we'll see what happens. Give it a few more seconds. Yeah. Elon Musk's what? Neural net? I don't know about his neural net. No, he said he's afraid of AI, but he is selling it. So, man, I don't know. Elon Musk is pretty much nuts. He says too many foolish things on Twitter. He's getting demoted from CEO for that by the Security and Exchange Commission. I'll start this up. Anyway, he's going to be not CEO, but something else. Maybe. Which one of these is not a buffer overflow defense? All right, and the point, this is the point, GCC is the compiler. And actually the compiler could protect you, but it doesn't. And that's where the argument is. These other technologies protect you. Some people think you should just make a smarter compiler, and that's effectively what Microsoft did. But GCC just compiles code without checking for this. Yeah. Address space layout randomization. That's what randomizes the code. These are good. Yeah, the address space layout randomization, data execution prevention, and canaries at the end. Those are the three main defenses. And GCC is the compiler that makes the code, and you could put a defense in there too, but people don't. But that's where Dan Kaminsky thinks we should be putting the defense. So the programmer doesn't have to think. Their code environment will just automatically put these defenses in there, and that might be right, but it is not what's happening yet. So which one allows code injection but prevents its execution? That's data execution prevention. That is the NX bit. So you define the memory region where you put the data as not executable, and then even if somebody injects code, it won't run. All right. Which one allows code injection but makes it hard to find? Okay, that's more clear. Address space layout randomization. So each process is at a random memory location, so you don't know where your code went. All right, which one detects stack smashing? That's the canary. You can get it by process of elimination, but that they call it stack smashing. That detects when you have somehow written past the variables into other control structures that you were not supposed to be changing. All right. Cisco has a similar defense in their routers called check heaps that walks through the heap to see if anyone has overwritten the pointers to the next segment, which indicates that somebody's been writing where they weren't supposed to write. All right, what language looks like that? Well, that's brain fuck, which nobody writes serious code in, but you know, it does demonstrate sort of the essentials of programming. All right, and I don't think I'm going to do any more. I'll just clean up and go to the lab and see if anybody wants help there. Let me get my winners. Chris C. I still don't know who I'm Not Steve was, so they're not going to get points unless they tell me. We do have a Steve, but he heroically did not claim the points, which he could have employed social engineering and claimed to be Steve, and I would have believed him. But he abstained from that. He could tell me that's the name he used. Anyway, so I'm going to stop the share, and I'll go to the lab. Here comes a chat message. Maybe it'll tell me who Steve is. Isn't Node.js a good thing? Yes, Node.js and Angular. That's why JavaScript is super important these days. There's a whole bunch of JavaScript-based frameworks. And it all happened because JavaScript was sped up by 100 times with Chrome and Firefox compared to the very slow Internet Explorer JavaScript engine. And then it became possible to do all sorts of exciting things in JavaScript. So it is very important for web development, and it does come with vulnerabilities. And I'm seeing it in the CTF. So that's the frontier of hacking. Hacking Node.js and Angular. Your pages certainly look more beautiful in it, so it is very popular. You're a much better developer by using them, but you can also make some interesting new mistakes. Anyway, all right, I'm stopping the share and going to the lab. All right.